There are many available technologies, starting with cloud solutions and libraries framework, how we can already employ the model itself. And in my approach, I don't do technology first or product for a product. I always like to know what is the value of this endure of this work. And I found I usually start new projects with lots of questions, and I found that when I ask why, rather than other questions, I think about the reason. What is the value? How gives understanding of the technology, and if I would develop technology, that would be my question. And another important stuff when you start the project is thinking about your audience. Who are those people who have the problem, or what are they doing? Be very specific and concrete, and try to solve the problem, not the problem you invented, but the problem that is actually on the market. And you know that there are another solutions rather than yours, maybe without machine learning, but you know you want to solve the precise problem. And there is a template, and if one of you want to try this template, just let me know. But for example, a group of people at the clinic suffer from epilepsy and come to the clinic to be diagnosed with the epilepsy, and solution is fulfill lots of questionnaires, have the evidence of their aura and attacks, do EEG test, do fMRI test. That's how they solve the problem. And why do we want to? The problem is in diagnostics in that case, and how to solve the problem is to build a model that do diagnostics for these people. That's how this schablon works. When you fulfill this story and you do your storytelling stuff, you understand why do you solve a problem, you understand who is the domain expert in this, you understand your sources and maybe potential resources, financial or domain expertise, to whom you need to talk. It works, for example, if it's a supermarket wants to increase the sales, so it's not a problem, they just want to do something better than they do now. And for that, they will send us special offers. And we know that we can customize offer with machine learning. And then we start to think about what data do we need, how do we want to work it out. When you already have a concept, it's good to make a research of previous solutions. And my first source of research is people. I usually ask how they do it, what are the problems. And the second obvious is ask Google. And those are the great machine learning sources that I'm using every day. Google Scholar gives the citation of the research work, and they have a ranking, so you know what is up to date. You know who is the leader of opinion in that model or that specific domain. On GitHub, there's many solutions that have an open source license, and you're free to use this for different purposes. Other are blogs, website with content, and those are all links. And I guess you would be able to follow the links if you're interested. So when you ask questions, don't propose the answer. And if you want to know how to analyze something, just type the problem. If you type a solution, you will go directly to the solution itself. You won't solving or doing your product. You will stick to the technology. So next thing is how to split the problem, and how not to be general and not to try to help everyone, but want to build a precise solution, to build a pill, not a vitamin. And in machine learning, it also divided by different criteria, and those are what I use. When you work with data, you usually know the sources of data, and you know the process. And for example, you understand that at stage A we have the cookies, at stage B we have the shopping list, and something like this. There are different conditions for target actions, so we can apply conditions. And if you analyze, for example, natural environment, there is a dynamical behavior, dynamical conditions. For example, how water go to the ice condition and change itself. So think about what are the statistics that describe what you're looking for, and that will help you to split the problem and have modularity in your work. Any questions so far? For example, if we back to the supermarket and imagine all sources of data that they have, how would you split data for clusters, or how would you split the project itself? What would be the stages?
Is that a question?
Yeah, it's a question.
You do it by like aisle or something like that, or product type, or like maybe vegetable or snack or something like that.
Mm-hmm.
Yeah.
Yeah. So we can cluster by type of food that, or type of goods that people buying.
Yeah. Yeah.
Yeah. Anything else?
What do you mean by dynamic behaviour? So I understand when you say splitting the problem down in terms of understanding the sources of information, because that is what you're going to use to solve the problem.
Mm-hmm.
And understand what you mean by target actions,
like
what you want a successful solution to be doing
in
terms of its output behaviour. But I'm not sure I understand the last bullet point around dynamic behaviour.
Well, for example, if we analyze EEG signal, that's encephalogram, that's scanning the brain waves, we have a dynamic of the waves when we are sleeping, when we're waking up. Those are different fluctuations and different. You can see it on the line. It has a different statistics and different behavior. Another stuff when you drive airplane, and when you're on the ground it's one dynamic, when you're in the air you have different dynamics, and your sensor will show you different various data, and it's nice to split them and understand, so this is normal for that stage and this is normal for that stage.
Okay, so it's not an individual number, it's how different variables can vary, and they might be different in this phase and different in this phase. Okay, I think I understand that.
And it's actually very interesting when you if you don't split, you may end up thinking that you have something abnormal or you have noise in the system, but that just have a meaning of changing the nature of the process itself. So when you did your research and you understand the process, you might want to develop a hypothesis. And you can formulate it mathematically, or you can formulate it like a story again, and those set your expectation. For example, you said that if I see that these two variables has correlation, that will mean that. So you're expecting to see something, and that's the moment that you try to catch. You can prove wrong, you can prove right. It's worth to write it down for a next iteration. So between this iteration, you do analysis of your hypothesis, what proved wrong and what right, and try to think what was the problem, what caused the problem, and amend your experiment. There is also null hypothesis in statistics that show that there is no significant difference between specified features and results that you have is observed only because you have error in experiment, or you have any other kind of error. So that's worth to know, that if you don't prove, just check if you didn't have any errors in your measurement, for example. The next stage is, because we are developing the system we are developing the real system. We want to know what are the system requirements. There are many questions, but I take something what usually what in my experience changed the way I work with data. For example, when you work with medical or personal data, you have to have a special license, and in order to get it, you might wait for a year or 3, or you might pay $1 billion or something like this if it works with health or treatment or pharmaceutical business. It's important to understand whether you will be able to get the data when you set up your team and when you have everything ready. It's also important to check if you have open data source for your task. For example, if we take EEG signal, there's open data sources, and there is a bank of open data sources, and there is a reason. When you develop a model, you want to have a benchmark. Sometimes you don't know what is good, what is bad, and you want to know what are the other results, and it will navigate you in your analysis. Another question is, what is the size of data? To train deep networks, Google use billions of data sets, and some models don't require as many data points. It's important to understand what is the size, because you want to operate it offline or online. So you need to store it. If you work in the cloud, you need to buy a storage for your entities. And you need to understand, if you update the data, do you need to store the old data, or it will grow exponentially? How many connection points to the model? Let's say if you have a model, and do you build a model for every customers? Do you train model for everyone, or you have only one model that have one endpoint on a website, for example, and when people use it, they see their result, but you don't retrain this model for everyone. You just use the trained model. That's an important question, because it helps to understand what are the computational costs. If you have one too many or many too many, you just multiply the computational cost to amount of your end users. What computational cost of the model you plan to employ? That's a really hard question, because you need to measure it, and it's when you do small experiments, you don't know how to extrapolate your measurements to the big data set. So I don't have answer to that question, but
I'm just going to ask that question.
Yeah. If I know, I would tell.
So it's for a lot of models, you have the theoretical results, right?
Mm-hmm.
Like if I'm using Gaussian processes, I know that it scales with the qubit and cube. So, but there's some other models it doesn't. If you're doing deep networks, then it depends how many layers you have.
Yeah.
So I think you can estimate because you know the order. But some models you just don't really know.
Yeah. it's good if you can estimate it. Sometimes you're working with a black box of deep neural networks, and it can grow exponentially, it can grow linearly, you don't know. And that's another reason why you want to have a benchmark from other people, how they treated their model and what results do they have. And computational, when you do this cost and do a small experiment, you can understand where to look for. So start with small data sets, don't train on the Google-sized data. The model brings value to the research or to the product, to the business when it's deployed and connect to the customers. And it's important to keep it in mind what would be your costs, and maybe at that stage you would like to amend your experiment or your hypothesis or something. So you can drop at any step and start again with your expertise in that task, with your knowledge. So preparation of data, that's a topic for the whole conference, I guess. There are several steps when you prepare your data set. As I said, we know what kind of data we want to collect. We either build API or we download it or we have online access. So we understand how we collect data and how we store data. Then when you receive your data, you need to transform it, because sometimes you have lots of NA or lots of noise. Sometimes you have missing data. Sometimes you have different formatting of the data. So you need to transform it to the format your model will understand. Usually it's table format, and you transform everything clean. Then after you have clean data set, you start to explore it. And for exploration, there is statistical learning techniques, how to understand what is mean of your data. Do you have any trends or patterns? Do you have noises? You collect all the statistics for the data source and create your own expectation what you can collect with this data. Sometimes when we want to extrapolate a data set to the bigger data set, and for example we want to analyze weather, we use weather for Cornwall, but we want weather for Europe, and you need to understand what are the difference between these data sets. Do they have the same features that will give you the outcome that you want? So it was to explore the statistical features. Then check consistency, if it's enough data, if the data include the features that you're looking for. For example, you understand during your feature engineering that one variable, let's call it A, give you the predictions that you care about. It's not worth to take all the rest of the parameters to predict to the prediction model. It will increase computation cost, but it won't give any better results. Improving data is when you change the format, change something, change statistics, do normalization of your data set, understand the deviation or distribution of your data, and you just improve it and make it similar. So you compare similar to similar. After you already have your data set, you will need to split it to usually to 2, but it's highly suggested to have three dataset: training, verification, and test dataset. Training is what you feed to your model during the training, and verification and test are unseen data. Why it's important to have verification data? It's because when you train the model, you learn the parameters within the model, and you want to check during each iteration if your model is okay with unseen data. And for example, if you have a big loss as a metric for this unseen data, it's better to understand during the iterations of the learning than when you give the test data and you fail the experiment itself. Any questions?
I think in my mind, in my limited experience, there's one kind of work where you're trying to build a model to give you the answer or the outputs, but sometimes you're just exploring data to see if there's anything you can learn without knowing ahead of time what pattern there might be, what useful information there might be. Now, in that second example, I don't know how to apply these ideas of understanding, if you've got the right data.
Mm-hmm.
It seems a little bit kind of random to say, got a bunch of data, it's relevant to the problem domain, like it's shopping habits or something. I don't really know what I'm looking for, but anything that I can find that's a pattern or correlation could be useful.
Mm-hmm.
Are there any thoughts around how you approach that second scenario with
Yeah.
this discipline?
So that would be the goal, to recognize a pattern, and for that there are also many models within machine learning and statistical learning how you detect the pattern. So it's not a prediction, it's just the feature engineering. You apply it and you see the output. It works exactly the same. You want the only point to have this preparation step, that you have a clean database that you can access, and you're sure that you use the right data itself. And the model can have different goals, like define the clusters, find a new pattern, or maybe predict something, or generate something based on your data. Yeah.
So feature selection is, to answer this question, the feature selection does become harder in that case, because of course, yeah, you can like do a PCA plot and you get your PC1, your PC2 or whatever, and you know that your PCR1 is made up of mainly feature A and feature B,
Mm-hmm.
but it's usually because it's a linear combination, then it's quite hard to say I'm only going to retain feature A and feature B, because when you go down the PC, like PC2 might still use all of the other features but at different weights.
Yeah.
So it's definitely harder when you've got this kind of like unsupervised problem that you don't know.
Yeah.
And the biggest problem, and I mean this is something that is probably the problem with big data in general, is the whole causality thing, and which strips a lot of studies and things that I've been involved in as well.
Mm-hmm.
In obvious things like, if you're looking at shopping trends, for example, and of course you see different shopping trends around Christmas, you can really confidently say it's because it's Christmas, everyone's buying other crap rather than just their usual shopping. But if you're looking at ECG signals, for example, and you try to correlate that to some gene expression or some, like mutations in the
Mhm.
DNA or something like that, then it's much harder because you don't know what's actually causing what. And as far as I know, there's not that many techniques in kind of like big data to deal with kind of this causality problem. And
Mm-hmm.
sometimes you just end up finding patterns, but you can't really explain them.
Yeah. To solve causality problems, there is Bayesian networks, and we will see some examples of what are the models to solve that kind of problems. But in my experience, I never had the only one signal that was proven that it will give me all the answers. So usually I carry lots of data, but I just drop something what is obvious will not help. sometimes I guess you can drop something important as well. So
Yeah.
chances are we never know.
So about effect size as well, right? And that's the problem sometimes in some fields. Like I work in medicine mostly, and people care about small effect sizes because even if a vaccine is not perfect, if it's gonna increase your chances of surviving malaria, then people are gonna hang on to that. Whether like probably in industry, if it's gonna cost you this much to advertise something that it's only gonna give you a return of an extra 1%, then it's probably not worth it because got of like cost benefit analysis at the end of the day as well.
Yeah. And it all depends on your initial resources. If you can, why not? The next stage is the most magical stage. So everything what was human understandable. Well, as for me, start crushing, because sometimes I have a result or plot from the model, and I don't understand what it does, even though I develop it myself. So in the training, when you train models, there are variables like parameters, and there are also parameters that model learn during the training process, and there's hyperparameters which are show you evaluation. Usually it helps evaluate the problem. So for example, it might be accuracy or cost function or loss function. That's something would help you to manage the black box. Learning variables learn directly from the training data, and hyperparameters help to make a decision about the model. So then after we decided what is the design of the model, what the architecture of the model, next step is the fit training data, and here you either fit training and training data, or you fit training and validation and scene data, and you set amount of iteration, you set the size of batch, how you train the model, and just click run and wait several days and get your results. It's in most of the I use Keras and TensorFlow. You can set a parameter and see the logs of every iteration and the estimation of everything. So it's kind of help to keep track on what you're doing. After you train the data, you do the final validation of the data. When you have your results, what is for example, loss and accuracy for the training, you store it into some you store it somewhere, and try to I use the word predict. It's not quite a good word, because you might want to detect a pattern, or you might want to do something different. So let's say you ask a model to do what it was designed for, and you have your results, and you can evaluate your results and understand, was the model overfit, was it good or bad? Maybe it was specified only for your training data, and can't understand the test data. And another hint, when you split the data, if you can do it randomly within the data set, it's better to do it randomly. Or if you can just choose something what is similar, but not equal.
Interrupt and ask a question like that. Are there different approaches to splitting your data into a training set and a test or validation set? Because you can just say 80-20, but are there more sophisticated approaches to say, actually, it should be 60/40, or it should be random sampling every time, or are there different approaches?
I worked with data series during my career, so it's really hard to randomize the signal because you will change the pattern of the data series. So what is possible to do is split the data to some windows, meaningful windows, and then with these cutted pieces define which one were randomly, absolutely randomly. That is what I use. If there is no restriction as a window, just use randomizer, or maybe some features, but I would expect to have the same feature.
Okay.
There are several ways, because you can either do like cross-validation, like split your data into different folds, but you can use bootstrapping as well. So some people, there's all sorts of theoretical results that, you know, bootstrapping sometimes is better. So if you use random forest, for example, data, you do a bootstrapping, which basically you're training on a data set which is the same size as your original data set. It's just that some rows are repeated.
Right.
But you can only use that if the order of the rows is not important.
Yeah.
So like as Aleksanda mentioned, if it's a time series, then of course you can't do that. You have to do windowing stuff. Yeah.
Okay. Yeah. Thank you.
There is a method, if I'm correct, it calls narrow window, when you select your data set and then you train and you try to expand this window. That basically that helps me. It helps to debug fast, because if I apply my gigabyte of data for the first run of the model, I will wait until it crashes and I will just lose the time. So sometimes I use teeny tiny data sets when I just want to understand that model is working as an algorithm. It won't show any significant result, but it might just demonstrate that you're going to the right direction. Another hint that is really important is to save your model. It helps. For example, you have several models, and you don't want to run from the beginning every time. You just save the model when you have your parameters, and in another function you download these parameters and use the model. It helps to save computational cost, and it also nice to have the saved model once you want to compare results, benchmark your results. You download it all and create a report based on your saved models. So if you can save, just save. Another tricky problem is how to evaluate the model. It's more or less understandable when you have supervised learning, but when it's unsupervised learning, it's really difficult. You don't know what is normal, what is abnormal. You don't know what's good or bad. And there is precision, accuracy. There are also sensitivity of the model. It's when you know what was positive, what was negative, and you calculate your true positive and negatives, and then you use formulas how to calculate those parameters. But precision usually show that if you don't change anything, how likely you have the same result, while accuracy show the closeness to the value itself. If there were a whiteboard, I would write a formula, but there is no, so I'm lucky. You can calculate another parameters to evaluate your model, and as long as it's meaningful for you. In supervised models, there is metrics that measure how good is your model. It's a loss function, which in optimization and in statistical theory, it show what is the cost of the wrong move. And with loss function, if you train network, for example, you have some optimizers that help to that help your network to train as fast as possible, and I really like visualization for optimizers that compare each other, and it shows how fast you go to the deep optimal solution. Accuracy is well when you have regression problem, or you want to create a new value, predict value. Sometimes accuracy doesn't work, so it will show you something around 0, but it's actually a good prediction. So it's worth to check if what kind of metrics people use to your model. And also, if you have your value, real value, and predicted value, you can calculate regression metrics, mean square error. There is around 30 different type of how you can calculate error, and some of them worth to try for precisely your data. For example, if you statistically know that you have a small difference, you use one. If you have a big difference between your data, you use another. So it worth to read this optimizers and metrics description and choose the one that suits your model. In unsupervised learning, such as clustering, for example, sometimes if you know the benchmark for your algorithm, you can go and use it, or you can create a fake data set and manipulate with some features, and for example, that it's surely divide to two clusters, and where's the error, where is not, and you run your model on those fake data. You measure, you do benchmark. Another matter is to hand label something. For example, if you know what is good or bad because of your domain knowledge, sometimes that's the only way how you can train the model. How you can how to validate your model by providing this expertise knowledge to evaluation. Cross-validation of different methods on the same data set sometimes helps to understand not only how good is the model and what you should choose, but it also show the parameters of your data set. So it's not trivial. It's usually meant to the problem that you try to solve, but those are methods that I try to use.
Can I ask a question?
Sure.
I've got two actually on that slide. On the supervised methods, you talk about the loss function, and you want to see it go down, and you can visualize it or monitor it, and that's a good way of seeing that your model is learning. And then on your third bullet, when you say regression metrics like mean squared error, are they different, or is that the same thing?
This mean square error it usually measures the distance between expected value and to the value that you have. So I would say usually it should be 0. That's the best answer, but it will depend on your data set and the model itself.
Okay. And your loss function can be that error, mean squared error?
No, this regression metrics, they calculated from the predicted or generated data. So you compare yourself, like what I predicted and what I have, or what I generated and what I have. Is it similar or not? That helps, for example, when accuracy doesn't work, but you still want to understand, do you have similar parameters? Did you generate similar parameters? You run another algorithm.
Okay. You have models where they're the same. So there are models that the loss function and the mean squared error is the same thing. So if you're doing like normal least squares, then they're exactly the same thing. The loss and the mean squared error is the same thing.
Mhm.
It's just that in machine learning you tend to penalize that loss function, so they're not quite the same. So it depends on the model. They could be the same.
Might be.
Yeah.
Yeah.
And are there kind of ways of thinking about choosing different metrics? So mean squared error is understandable to many people,
Hmm.
but some people choose, say, boundary cross entropy or other things.
Yeah.
Is there a way of thinking about this makes more sense for particular problems? So my naive understanding, because I'm not an expert, is if your output has to be one of many options, people tend to choose binary cross entropy because it penalises the wrong answer quite heavily. Is that a good way of? Is that how people do it? Is that how they choose the right metric?
There are research and articles about different metrics and how calculate them, and benchmark of those metrics itself within the model, and it usually has a description why it's better to use and what are the cases when it's better to use. So yeah, it's online available to find those.
Okay.
A lot of the time it goes into cost-benefit analysis again. So if I'm building a classifier, for example, so that to detect whether a particular tissue, whether it's got a benign cancer or an abnormal growth, then what's the cost and benefit of treating someone thinking that they have a cancer or not treating them?
Okay.
So Spiegelhofer wrote quite a lot of stuff about this. So about breast cancer screening in the UK, where a lot of women were treated when they didn't have breast cancer,
Right.
and actually it caused a lot more problems further on. But like if you actually waited longer for like a second test, the penalty for waiting to give them chemotherapy wasn't as bad as treating them when they didn't have it. So it gets very complicated there, especially if you work in public health, because the NHS doesn't have a lot of money. So.
Yeah. That is really fascinating. Thank you. Sorry to interrupt you there.
Yeah, I absolutely agree. It's when we calculate the accuracy of the method, we think about what is the cost of the mistake, and if accuracy is not enough to cover this cost, so basically you keep trying on experiments. Here are resources to develop a model. As you ask how to estimate company resources, that was one of the questions, and there are generally, if you have open data, you don't have to pay a license. You generally have a human resources and you have computational cost. And for human resources, those are four skills that need to be covered. Data scientists, sometimes the data scientists itself is split to data engineers and data architects and data scientists. So it might be one person, but it might be a division of 100 people. Those specialists has different skills. For example, software developers, they care about deployment to production and testing, and how to testers care about testing, but they think about how your model is available for your customers. While machine learning engineers, they develop the algorithm, they calculate, they evaluate, calculate, and do that kind of stuff. Sometimes it's not overlap. Sometimes it's overlap. If you're lucky to find a person that can do both. I would say that it's better at least to split data scientists with machine learning engineers because of the bias in reading data. Sometimes we can just skip some important statistics and apply it, and if there were two people, there wouldn't be that bias. So I would at least split these two. For computational cost, it's a cost of hardware. Recently I found a review of the comparing building a hardware on CPU and GPU, and for example, what it was an IBM, so some big company built a supercomputer which costed around $1 million, and MIT lab built it same performance supercomputer on GPUs which costed $30,000. So it worth to know the technology. For cloud, there AWS, Azure, IBM, and many other clouds. It might be cloud with API. It might be just a cloud. If you understand how to install your libraries, I would go for just a cloud, because most of the APIs they refer to the same frameworks that open source available. That was my initial plan to complete this, and I have also the overview of it's actually I found it's on a great source for machine learning. They have tutorials, and the author explain lots of models and provide the results and code as well. And I found this overview of machine learning methods. But before we do this overview, maybe you want to talk about the building of intelligent system. Maybe we can have some discussion.
I have lots of questions, but I won't hold the conversation.
Maybe you can start.
So did you have...
No, go for it.
So one of the things you mentioned on a previous slide is hyperparameters, and I haven't found a good answer to finding them other than trial and error. So, for example, training some kinds of like two neural networks competing against each other in a GAN, generative adversarial network. There doesn't seem to be a good approach to finding the right hyperparameters, or optimal ones, or cost-effective ones. And I don't know if you have any thoughts on what people call hyperparameter search. Is there a good discipline around that?
I never heard about the discipline.
Okay.
Yeah, I usually look what kind of hyperparameters developers use at the open frameworks such as Keras, TensorFlow, PyTorch. What do they use? They have a description and benchmark for those hyperparameters. I never developed it myself, so I don't have the precise answer. But maybe if you see some pattern, maybe it's worth to start collecting the data during the training process and then employ it as a hyperparameter.
Okay.
So that's why you have a validation data set. So you can learn the hyperparameters using cross-validation on that validation data set.
Okay.
So, because if you're using a very complex model, then your loss function, you're always going to minimize that to zero. Like you can always come up with an arbitrary complex. Basically, you're just joining the dots.
Yeah.
Whether that validation data set will basically, start tapering off, and then when the model becomes more and more complex, it's just going to start shooting up. So, and that's usually your cutoff, and say, okay, these are the hyperparameters that I'm going to choose.
Okay.
So, and this is the same if you have two competing networks. You change the network, and then you can compare the different performances.
Okay.
But the validation data, like doing cross-validation, is key, because you really don't want to be doing trial and error, ideally, for those cases.
Okay. Yeah. That's useful. Just expand on that a little bit. I think with, say, training, say, a network to classify, you can start big, and you say that's expensive, and then you can say I can make the network smaller, so it's cheaper, and it still works well enough. You might find it works even better. So you can plot that graph, which is nice. But I think some architectures still behave in ways that aren't that predictable. And I think that's where it's hard to say, you know, if I gently reduce the size of the graph, it doesn't behave kind of in any predictable way.
There is a beautiful page on Reddit, and people submit pictures of plots of loss function during the training, and those are amazing because it's sometimes it's impossible to understand what had happened. Maybe you found the data that have distinguished features other than the rest of the data set. Sometimes it's get overfit and grow. Sometimes something happening. So it's
really funny. I've seen it.
Yeah.
You should share it. Well, it's really good.
But that's why I think the exploration bit is the key point, because I think the problem is with training these data sets, you want a rich data set. It's not about how big the data set is, but how rich it is. So if I'm building a classifier that differentiates between a dog and a person, for example, you know, dogs have really distinct features compared to human beings, but I don't want to use just German Shepherds or just poodles or whatever. So I want my data to have loads of different kinds of dogs, because there are dogs which are as big as humans, and those are the ones that are going to cause me a lot of problems. So actually, you know, there's also a lot of this exploration where people tend to actually try to pick the problematic data points, because you know, a poodle versus a man is going to be very easy to classify, but I can't remember what they're called, you know, these big dogs that basically grow as big as humans, those are the big problematic ones.
I don't know if it's still a problem, but well, one of the first results in deep networks was on the data set they have pictures of people with white background, and when they had the real data, nothing was recognizable because background was different. So
yeah, I don't know if you're aware of one of the first uses of neural networks by the Pentagon. You ever heard the story? Yeah, so during the Vietnam War, they really struggled with the Viet Congs like ambushing them. So they wanted to design a system to try and identify like tanks and I can't remember what they used like as machine guns, the Viet Congs. I can't remember the exact name, but basically tried to do that. So they took loads of pictures of like basically trees with either people and arms in it or without, and they trained this neural network and it performed brilliantly. And they were like, oh, this is amazing. And then they decided to basically commission another set of photos, and they applied the model, and it failed like completely. And the issue is because whenever they took the photos with and without them, one was a sunny day and the other one was a really cloudy day. So what the neural networks actually picked up was the really nice and sunny day rather than the other one. So
that was the real feature.
It's a shame it wasn't Trump president back then. Yes. That was a brilliant story.
But there is an interesting question around trying to work out what the models have learned. So one of the points of these approaches is you don't want to spend too much time handcrafting a model. You want it to learn by itself, but you want to check that it hasn't learned the wrong thing. And again, I don't know if there's any good discipline around just checking that it hasn't learned the background, or I guess it's validated. Make sure
I mean, Google the Dream Mind generator, I think it's called.
Deep Dream.
Deep Mind,
Deep Mind generator, I think it's called. So you ask the reverse question. So you say these are the features that are correlated to a dog. You give it a picture, and it enhances the regions where it thinks there's a dog. So, and that's like one way to actually figure out what's it's actually doing.
Yeah.
So, but yeah, it is difficult. Yeah. And this is why I struggle to use, like I don't tend to use neural networks in my field, because it's medical, and what they're interested in is knowing, you know, what is actually, they want to rank the importance of you know, like which gene is actually more responsible towards this immune response, for example, or, you know, if there's a correlation between I don't know, smoking, and so between like lung cancer and a bunch of other variables, they want to know which is actually the most important, because of course age is a problem, smoking is a problem, alcohol is a problem, but which one is the most important? Is it alcohol, is it smoking, is it a combination of both? So, but if you just tell them, oh, you just have a neural network and with different weights, they don't know. So, but it's horses for courses, yeah.
I know that I didn't read the research itself, but I know that some people try to reverse engineer the network, because when you cut it to the layers, you actually understand the mass behind it, and you can distract some knowledge from each layer. I didn't see any result itself, but I know that it's possible for some network.
With image analysis, because you're learning hierarchy of features, so I can understand that works quite well with image recognition. That's a good idea too.
And there is playgrounds for networks, and when I don't remember what was the website, but you can add layers. You can it's very famous, and it shows what kind of gradient is learned at which layer, and you maybe it's that direction of learning.
Okay.
Any other thoughts, maybe? Or what you will try to apply to your project, after all? At least anything.
Currently I'm doing something very different from what I usually do. I've just got a lot of JSON files of tweets because there's a evolutionary biologist, sorry, culture evolutionist, I think that's the word. Alex?
Basically.
Yeah.
Mm-hmm.
Is that a word, cultural evolution?
Yeah,
yes, that's the word, yeah. They're all biologists to me, because I don't understand the differences. But they're basically interested in doing a lot of sentiment analysis on tweets to see how the public's perception on climate change is changing over time. So we've been collecting tweets since March now,
Yeah.
and we kind of like want to see like what's the effect of the Netflix series, for example, the David Attenborough one, Our Planet. What's the effect of Greta Thunberg, like, and try to understand these things. So in that case, it's not a supervised problem. We just have a bunch of tweets, and we just want to like cluster them and see what people are talking about, and then try to infer where these messages mainly come from, and also like flow of information, which I'm not entirely sure how we're going to do it yet, but whether a tweet will go viral mostly because it comes from an important person, like if David Attenborough tweeted compared to me, no one knows me, but everyone knows David Attenborough, or whether it's to do with how shocking the message is in the tweet. So, which I think it's a combination of both, because if it's a shocking picture or something, it tends to go viral quickly, but also if it's being shared by a famous person like Beyonce or whatever.
Maybe another way how it goes viral is that how many influencers does it reach on the way, and if we recognize the social networks, there are some points that are connected to the most, and those points are very important in many fields. In cybersecurity, for example, that point has the most security because it's the center of the system. So interesting.
Unfortunately, I don't know much about networks, so I'm starting to learn a bit more about that field, and it's a minefield, to be honest.
Just try. There is no other way to understand how networks works. Just find the model and run the model with the data set, and you will gather the intuition during iterations.
I think to answer your question about how we're going to use this, I think for me, a lot of what you've spoken about applies not just to fancy machine learning methods. It's basic science, isn't it? It's and being clear about what are you trying to confirm evidence for using statistical measures? How do you decide something is, of statistical significance? Questions around data diversity and quality, overfitting. Those kinds of challenges are kind of, if you took neural networks out of the picture, those questions are still really valid. And I think there's a lot of hype, I think, around the words AI and machine learning. But take that away, there's still the scientific discipline and the statistical discipline is still there. And I think for me, thinking back to basics is really important, and applying a kind of skeptical mindset to say, just because I've pressed train or pressed go, what's actually happened? It's given me a number, but why do I trust it? And being the skeptic yourself around your own data model and your own sort of machine learning model is really important, I think. So I think it's really valuable to be brought back to those kind of essential basics again. I think that's really important.
Thanks.
That's why we're trying to move away a lot from this kind of like hypothesis testing, because I mean we still have this problem in academia and peer review where it's all about the p-value, this magical piece more than 0.05. But as you were saying, it's most of the time it doesn't mean anything, because what really matters is your effect size. Like, how big is that effect? Is it what's the practical significance of that meaning? Yeah. So I remember when I moved down to Cornwall 5 years ago, like all my friends were joking. They were like, "Oh, you're going to get lung cancer because like it's a hotspot for radon." And I googled it because I was really curious about it, because I know nothing about radon, right? And you go on the Public Health England website and you can actually see a map of the UK, and Cornwall is this massive red blob of like big radon, and it's like, oh my god, this is crazy. And then you actually look at the risk factor, and they've got this like bar graph. I can't remember the exact number of the odds ratio, but it's like the chances of you having lung cancer if you smoke, and this bar chart is like this big. And then if you lived if you're exposed to radon all your life, and it's like this tiny little bit, and then if you live anywhere else without radon, it's like a flat line. It's like, okay, I think I'm safe. So. And that's usually the problem, is that's why a lot of papers in the past years have been retracted from like even Nature, and and it's problem with climate science as well. Like, one of the biggest issues in climate science is not understanding the limitations of the model. Like, a lot of people treat the model as reality, and we know from climate science, for example, that we can't really model albedo effects really well, or and things like that. And you need to keep that, as you said, you really need to keep that in mind. And
I think you made an interesting separation also between fancy statistical measures like p-values and things aside. What's the practical effect? And if it's right for your business or your job, and you can measure that, tell people's health or whatever, that's more of an important measure than something that's encoded in Greek letters.
It is. The problem is this subjectivity, right?
Yeah.
And that's always been the problem, and that's why p-value has been used a lot in peer review of like accepting or rejecting a paper, because it's objective in a certain way, where they're like, if my effect size is 10%, in my eyes 10% is a lot, whether like maybe 0.1% is a lot for someone, because if it's, I don't know, to do with the efficacy of a vaccine, for example.
So maybe the answer is that if I said to you, the answer is p is 0.6, that without context doesn't mean anything.
No.
Whereas if you contextualise and says, that means 1,000 less road deaths. So I think the lesson for me is those pure metrics on their own aren't that useful, but contextualised back into the problem domain, it might be a saving of 0.01p for tax. That's nothing.
Yeah.
Whereas the effort for doing that might be huge. Whereas if we say it's 10,000 less road deaths just in Cornwall, then I think that's a really useful insight. I think the other one we haven't touched on yet, and it might be something for another day, is the challenge of causality versus correlation. Maybe that's something to do just after Christmas. That's a really important one, I think. But thanks for kind of bringing that up.
Yeah, December is a good month to do this kind of topic, because you want to understand why you end up here in a good place.
My favorite one is Nobel Prize winners versus consumption of chocolate. There's a positive correlation.
Is there?
Yeah,
right. Okay.
It's because you had a lot of Swiss Nobel laureates in the past. So,
application for using AI. A lot of businesses, and certainly the big organisations, have a massive backlog of old applications, old software, legacy software, and it costs a fortune to get it rewritten and brought up to date. And it's usually something that gets parked in the corner, and it's usually labelled as technical debt. You know, it costs a fortune to maintain, and nobody wants to touch it because nobody's documented it. Or it's so long ago that but it works, don't touch it, kind of thing. So there's an application there for going through and understanding exactly what the logic does and how it works, and then rewriting it into a more modern language or in another sense. So I don't think AI has really been used much in that regard yet. I've been looking into it. It is quite a can of worms because you've got all these different languages and applications and things, and there's a lot of interaction that goes on through networks and databases and all the rest of it. But it's an area I think that would probably be a very good application for AI. So this is the reason why I'm taking an interest in it. So I'm glad to come along. I've got a methodology to start with. Thank you very much. How far I'll get, I don't know.
What's worth looking at is there's a lot of probabilistic programming languages, for example, Stan and Edward, and what they actually do is parse a programming language into another programming language. So Stan, for example, is a probabilistic programming language that parses its code into C, and then it runs everything in C. So I'm not saying I'm going to solve your problem, but it's probably something worth looking at.
Worth exploring, isn't it?
Yeah, because it seems to me like what you want is something that parses whatever language is being written in, like Fortran or whatever, and then translate it into Python or something.
Or some intermediate code which can then be transferred into something else. But it's
It definitely sounds like you're looking for a dictionary or keys for a translation, and maybe if you can start with the most significant one and understand how.
Can you speak up a bit?
Yes. So if you can start with the most significant value and create a dictionary for this value. And apply translation, as you said, if it's programming language, you can parse it. If it's linguistic, you can translate it into something new.
Yeah. So you're saying create a dictionary?
Maybe. For me, it sounds like a good start, but maybe it's not.
It's worth exploring. Thank you.
If it's a popular language, I would Google it first, because I don't know what language is it written in. Do you know?
There's a lot of other stuff in COBOL and other languages and stuff.
I know there's a lot of stuff in Fortran, like people have written.
Certainly on the scientific side as well. Fortran.
People have written stuff that translate Fortran into C.
Because last year I worked as a project manager for Cornwall Council. I came out of retirement, took this job, installing, updating a lot of their infrastructure hardware. But they were moving applications to the cloud, putting things up in Microsoft Azure. But it was proving quite problematical because applications that are written, often standalone run on servers, things like that, aren't used to running. They have load balancers, and when you try and put it in the cloud, they don't quite work. And then you've got, well, what does the bloody app do anyway? So it involves a lot of understanding, a lot of testing to actually make sure it does that thing written 20 years ago still work and do what it's supposed to do, call the right database, throw everything right on the screen. So yes, they admitted they had a huge problem. They've got sort of like 100 odd applications which are that are probably fairly ancient. They're paying through the nose for some organisation doing things for support and stuff, and not quite sure what it does. As to moving it to the cloud, it's not that straightforward. Or you have to go really lash out and very high availability storage to make sure that it doesn't fall over. So so that was, although I was involved with replacing their storage area network and things like that, which are very much more hardware related, but I could see the software problem.
Mm-hmm.
Yes. So, anyway, thank you.
You're welcome. I will just show you those two links. To know how to. One is, the name of the first one is Network Zoo. I don't know if you can open the link or not. Can I?
Should be able to. Is it the code's not working?
Doesn't seem so.
Maybe copy and paste into the right click. That's it.
So on that website, they do have different design of the network, different architecture, and they also have a description what each layer does and how to understand what the network capable of doing. They do have names of these architectures, and if you Google it or use the resources that was on the second slide, you might find the GitHub link with this architecture. And investing around 20 minutes, you can plug this model and run and see what it's doing on the test data. Another link is this is a very good source, and there are description of type of learning, like supervised and unsupervised rainforms or semi-supervised learning, and it also combined by the function. What does it do? For example, regression algorithms, they try to split your data set. It might be linear, and you can apply it to deterrent data, for example, or it can do help in clustering when you try to build a plane between two data sets. And there are good concise description of methods, of class of the methods, and I think I will post the presentation on my Twitter, and you can find, and maybe we will send the presentation. I don't know, but it will be on Twitter, and
Definitely share the presentation.
and you can explore those sources and how to manipulate with yeah, this is my Twitter, and I will download it.
Brilliant. Fantastic. Thank you very much.
Thanks for your attention.
Do you want to do a few more questions? Or?
Yeah, if you have some.
With the slide about the number of connection points, could you give another example of explaining that?
Which one was it?
The fifth one, was it?
It was about splitting problem. No?
It was connection.
This
How
one.
many
Yeah.
connection points?
That said how many do you train a model for each client or for each person? For example, if you analyze some medical data, maybe you train a model for a group of people, and you know their parameters, for example, age or disease or something, and then you substitute you apply the new data to that one model, and you receive the answer. But maybe you want to build a model that will learn from the personal signal itself. So you will run the training for every person that want to have the outcome of this model.
Okay. personalised medicine, would that be?
Yeah.
Okay. Right.
It might be. I see how applied to medicine, but I guess you can apply it for different supermarkets differently. So, for example, if you can uncover someone else's data and you don't want to have any correlation, you might want to train separately on the data sets.
Right, thank you.
Are you using this approach in your current day job at the moment?
Yeah, and I use it because every data series comes from different engine, comes from different data source, and they have a common pattern, but they have this common pattern is so small. They have so many different patterns, and I have to fit it to every source itself.
What sort of projects do you work on?
I'm not sure that I can tell right now because it's not deployed yet. Data series analysis, yeah.
It seems like this connection problem is more about making sure that the distribution of your data is the same, across your testing and your training, because that's usually one other problem in machine learning. Like if you train using a particular data distribution, and then you expect on the field to collect a very different distribution of data, then these models aren't known for doing very well at extrapolating, for example. Like it's okay for interpolation, but extrapolation.
Yeah.
So for the supermarket thing, for example, if you had data from Tesco and Waitrose and Sainsbury's, would you build a model separately or would you combine all the data together? Now, if you have some knowledge, like for example, Asda and Waitrose, they serve very different clientele. Like people go to Asda, people go to Waitrose. In general, they're different people are going to buy different things. So if you combine the data together, you are probably going to pick obvious trends, but you won't be able to pick the finer trends, which you probably get if you do more individual. And then location as well based, Like I'm sure the Asda in Penryn is very different from Asda in London, for example. So then you end up in this problem of like, at what point do you stop, because you can start going into like regions and like street level.
Yeah.
Which is always a problem. With big data and medical as well. Like, if I'm looking at correlations between certain diseases, like, do I do it on England? Do I do it on London? Do I do it on the whole of Europe? So, and then how generalizable that answer is, it's always a problem.
Someone emailed me a question ages ago, 3 years ago, and I wasn't able to answer it well. And what they said, it was a student actually, secondary school student doing a school project, and they said this neural network stuff is great, but it's computationally expensive. And they said, why don't we? They asked the question: if we split the data and put a tenth on that machine, a tenth on that machine, a tenth on that machine, and run 10 different machine learning exercises, how can we combine the results? Is it possible to combine the results? And it really stumped me. I didn't know the good answer to that. Because obviously, if at one level it can learn the same thing, like the white background or the cloudy sky.
Yeah.
But you don't know what you're missing out on by separating out the data. It's a hard.
It's a bit like MapReduce, isn't it?
Yeah.
For AI.
Yeah.
It's always to do with the complexity, right? So I always compare it to a 1D problem. Like if what I'm trying to model is a linear relationship, then it doesn't matter at what point I'm chopping that data. I'm always going to get the linear relationship.
Yeah.
If I'm trying to fit a quadratic, and I chop the first bit, I'm getting a negative slope. If I chop the last bit, I'm going to get a positive slope. So, and the only way you can find that complexity is through your data exploration right at the start.
So feature engineering comes first, I guess.
Yeah.
But it's harder to do this way.
So knowing your data, knowing the problem domain, will always help you loads in the training stage, rather than naively jumping straight to the training stage.
Well, yes.
So understanding the shape of your data.
Yes.
That's the biggest lesson I've learned in 10 years is don't jump to the software or the library or the tool. Understand the data and anything that you can use from the domain will help you massively in the machine learning task.
Yeah.
That just keeps coming back and back.
Trust me, it's something that I repeat every single day. Like the amount of like PhD students or like undergraduate students that email me for like that support, and they come to me and they show me their R script, and all I see on their R script is GLM, GLMMM. So these are different linear models, generalized linear model. Like that's the only line of code that I see. It's like, have you tried plotting the data? No. So they just read the data and they fit a linear regression model, because what they're looking for is that p-value. And it's like, no, if I spot the data. So, but in terms of sharing information, there's a whole field now of machine learning, which I'm totally not an expert in. It's called transfer learning, which is quite good. So you basically, if I trained a neural network to differentiate between a man and a dog, I start with that if I want to differentiate between the man and the cow, because it has already learned some patterns which are common across animals, rather than starting from zero. And then that is one way to kind of answer your student's problem, which is you are kind of splitting the data at that point, because you're not using it. But
I know a little about transfer learning, but that you have a weight for each layers. And in convolutional networks, you destruct the last one and you train on the last layer, and you use all the learning that comes before.
So you've learned a hierarchy of features, and the lower level ones will be transferable to another domain. Shall we? We could carry on talking further, but I think we should probably call it to a close. Thank you very much.
Thank you very much.